We have laid the groundwork for the memory management. Now we'll explore the powerful concept of virtual memory. The term virtual memory refers to something that appears to be present but it is not necessarily. It is a technique that allows a program's logical address space to be much larger than the physical main memory available on the system. Essentially, when a process needs more memory than physically available, the operating system can use a portion of the hard disk as a temporary extension of RAM. This area is often called swap or backing store. The separation of logical and physical memory frees programmers from worrying about memory limitations and allows for more efficient system operations. The most common way to implement virtual memory is through demand paging. The core idea is simple but powerful. Instead of loading an entire program into the memory at start, we only load a page when it is actually needed, that is, on demand. This has several key benefits. First, it requires less I/O because we are not reading unused portion of the program from the disk. Second, it requires less memory, which means we can run more programs concurrently. This leads to a faster response time for users as programs can start running before they are fully loaded. And finally, it allows more users to share systems simultaneously. The main advantage is overhead associated with handling a page fault, which is the mechanism that triggers loading of a page from the disk. To implement demand paging, the hardware needs a way to distinguish between pages that are in memory and pages that are on disk. This is done using valid-invalid bit in the page table entry. When an address is generated, the hardware checks this bit. If the bit is set to valid, it means the page is in a memory frame and the translation proceeds normally. If the bit is set to invalid, it means the page either is not part of the process legal address space or is valid but currently on the backing store. And access to a page marked invalid causes a trap to the operating system known as page fault. So what happens during a page fault? The process of handling one is very specific as shown in the diagram. The memory reference causes a trap to the operating system. The OS must determine if the reference was valid. If it was an illegal address, the process is terminated. If it was a valid page that is not in memory, the OS proceeds to find a free frame in the physical memory. Then it schedules a disk operation to read the required page from the backing store into that free frame. Once the disk is read is complete, the OS updates the page table, changing the entry from invalid to valid and storing new frame numbers. Finally, instruction that was interpreted by the trap is restarted, and the process now can continue as if the page had always been in the memory. This flowchart provides a more detailed look at the entire process. A process starts, generates an address, and the hardware checks if the page is in the main memory. If yes, the instruction completes. If no, a page fault interrupt occurs. The operating system then takes over. It checks for a free frame. If one is available, it gets the disk address of the new page and reads it in, adjusts the page table and restart the instruction. But what happens if no free frame is available? In that case, the operating system must select a page for replacement. This crucial step is where page replacement algorithm comes in.